Swayam Prabha. Digital India. Educated India.
Last time we saw that the deviatoric part of the stress tensor sigma ij dash will have the principal directions and also associated stresses, which are going to be given by this set of equations, where sigma dash represent the principal stress and the principal directions are given by Lj. And also we showed that if Lj has components like L, M and N, then we are going to have this equation in this expanded form, and if we have to have non-zero solutions for the direction cosines L, M and N, we must have determinant of the coefficient matrix equal to 0. This can be written in the expanded form like this, which is very similar to the earlier case where we had considered the total stress and the principal stresses given by sigma, and these stress components were sigma x, sigma y and sigma z, not with the dashes. Now, this can be expanded, and if we expand it, it comes out to be like this: sigma dash cube minus I1 dash into sigma dash square minus I2 dash sigma dash minus I3 dash equal to 0. This is equation number 4, wherein again I1 dash, I2 dash, I3 dash are stress invariants, and these are given by I1 dash is equal to 0, because this is equal to sigma x dash plus sigma y dash plus sigma z dash, and this is nothing but sigma x minus sigma m plus sigma y minus sigma m plus sigma z minus sigma m. Since sigma m is equal to sigma x plus sigma y plus sigma z by 3, so this is sum of these three stresses will cancel, and therefore this is going to be 0. Similarly, the other invariance has the form as you have seen earlier. It is going to be sigma tau xy square tau yz square tau zx square minus sigma x dash into sigma y dash, sigma y dash into sigma z dash plus sigma z dash into sigma x dash. That is the second stress invariance, and we can now write the other component I3 dash sigma x dash sigma y dash sigma z dash plus twice tau xy tau yz into tau zx minus sigma x dash yz square minus sigma y dash into tau zx square minus sigma z dash into tau xy square. So, we can solve the equation number 4, using these coefficients I1 dash, I2 dash and I3 dash. Here, since I1 dash, we will get some advantage in solving this equation 4, and finally, suppose the roots are sigma 1 dash, sigma 2 dash and sigma 3 dash, then we can write that principal stresses for the total stress tensor is nothing but sigma 1 dash plus sigma m, sigma 2 equal to sigma 2 dash plus sigma m, and sigma 3 equal to sigma 3 dash plus sigma m. You can also, after having obtained these three deviatoric principal stresses, you can get back to the equation number 2. You can get back to this equation. Herein you can substitute the value of sigma 1 dash in these three equations. You can extract the roots L, M and N from these equations to get the corresponding direction cosines, and it can be repeated for sigma 2 dash and sigma 3 dash. So, this is the way how you can solve for the principal directions starting from the deviatoric part of the stress components. Next, we will consider transformation of stresses. So, we will consider transformation of stress tensor or transformation of stresses from one system of coordinates to another system of coordinates. Let us consider that we have three directions like x, y and z, which we can also write as direction 1, 2 and 3. Suppose the stress at a point P is given by the tensor sigma ij. You have 9 components of stresses in 3 dimensions. Now, we would like to transform these stresses to another coordinates. Let us say that we have another set of coordinates which is given by x dash, y dash and z dash. So, if the stresses are given in this system x, y, z, we would like to get the stresses in a system x dash, y dash, z dash, which are arbitrarily oriented with respect to the original system. Now, in the system x dash, y dash, z dash, we would like to write the stresses by this symbol sigma I j dash. Now, let us see how we can go about getting these stresses in system x dash, y dash, z dash. Let us write that the direction cosines of the new set of axes, say this x dash, this has direction cosines like L 11, L 12, L 13. So, these are the direction cosines of the axis x dash with respect to x, y, z. So, also the direction cosines of this axis y dash is L 21, L 22, L 23, and the direction cosines of z dash is L 31, L 32, L 33. Now, if we consider a plane perpendicular to x dash, let us consider the plane which is perpendicular to x dash. So, this is the plane A, B, C. So, this is the plane which is perpendicular to x dash. Then obviously, we can see that on this plane we will have the axis y and z lying. So, therefore, if this is the outer normal to the plane, then these two axes y dash is going to lie and on this plane. So, also z dash is also going to lie on this plane. Now, we can write the traction on this plane to be given by, let us say, S1 is going to be given by L11 sigma x plus L12 tau yx plus L13 tau zx. If we make use of the initial notation, we can write now little in a simpler form L11 sigma 11, L12 sigma 21 plus L13 sigma 31 and S2, the other traction, is going to be nothing but L11 sigma 12, L12 sigma 22 plus L13 sigma 32. Similarly, we will have traction S3 is equal to L11 tau 13 L12 tau 23 plus L13 sigma 33. So, these are the tractions on this plane. So, we are going to have the tractions on this plane to be x direction is S1, y direction is S2 and z direction is S3. Now, we can get the components of these tractions along the x dash. So, if we try to consider the component of these tractions in this x dash direction, that will give us the normal stress, or that will give us the stress in the x dash direction. So, therefore, we are going to get now stresses sigma 11 dash is nothing but it is L11 S1 plus L12 into S2 plus L13 into S3. So, if we substitute the values of the three tractions, we are going to get now L11 sigma 11 L12 sigma 21 plus L13 sigma 31 plus L12 L11 sigma 12 L12 sigma 22 plus L13 sigma 32 plus we are going to have L13 L11 sigma 13 L12 sigma 23 plus L13 sigma 33. So, this is what is going to give us the expression for the normal stress in the on the plane which is perpendicular to new axis x dash. Similarly, we can get now, so after having got this stress, in this direction by taking the components of the three tractions in this direction, we got sigma 11 dash. Similarly, if we take the component of those traction in the direction y dash, that will give us the stress sigma 12 dash. So, we can now write sigma 12 dash. So, for convenience I can probably write here, this is nothing but sigma x dash and this is nothing but it is tau x dash y dash, that is the stress, and this is going to be given by, we will now make use of the direction cosines of this y dash which is nothing but this set. So, we can now write that the component sigma 12 dash is going to be nothing but L21 S1 plus L22 S2 plus L23 S3, and again if you substitute the value of the three tractions that we have, what we find is nothing but this expression L21 L11 sigma 11 plus L12 sigma 21 plus L13 sigma 3 1 plus L 2 S2 is nothing but L 1 sigma 1 L 1 sigma 2 L 1 sigma 3 plus L 2 into L 1 sigma 1 plus L 1 sigma 2 plus L 1 sigma 3. So, we can get now the stress component sigma 1 dash, and you should have no difficulty in appreciating the fact that if we want to find out the component of the stress in the z dash direction, we can make use of the in the z dash direction we can make use of the direction cosine given by this set. So, this will give us the component sigma 1 dash. Now, all these can be written very conveniently by making use of the tensor notation, and it will give us finally that all these components that we are going to write, we can write in this form. It is nothing but sigma Mn. Suppose these are the stresses in the new system x dash, y dash and z dash, and we have the original set given in the sigma ij, let us say, and it is given in the system x, y, z. Then we can write the connectivity between the two set using the earlier expressions in a compact form and a generic form like this. Sigma Mn is equal to L Mi L Ni sigma I j, wherein all these M, N, so also I and j take up values 1, 2, 3. So, this is the transformation rule for second rank tensor. So, this is the rule for transformation of second rank tensor. Sigma Mn is equal to L Mi into L Ni into sigma ij. Now, I would like to illustrate this by considering some examples later, but if we want to write any set, it will be like this. Suppose we are interested in writing, so let us say we will consider example. We are interested in getting the new value of, let us say, stress 2 3, and our original set is given by, so sigma 2 3 new is what when we are given these values are given. So, again we will make use of the fact that the new set would have the direction cosines given by L Mn, let us say the direction cosines of new set. So, I can now write sigma 2 3 is equal to L 2I L 3j sigma ij. Now, this can be further expanded like this. We will have value of I varying from 1 to 3, so also value of j varying from 1 to 3. So, this repetition of indices indicates that there is summation implied. So, we can now write, if I take value of I to be first changing. So, therefore, I can write this thing as L2I, I am sorry, L21 into L3j, and this will become 1j plus L22 L3j sigma 2j plus L23 into L3j sigma 3j. So, you can link it up that these are nothing but actually the tractions, these bracketed quantities are nothing but the tractions on the plane which is perpendicular to the direction 2. So, therefore, we can now expand it further. This is nothing but L21 into, now j can be given values from 1 to 3. So, therefore, it will be L31 sigma 11, L32 sigma 12 plus L33 sigma 13 plus L22 L31 sigma 21 plus L32 sigma 22 plus L33 sigma 23 plus L23 L31 sigma 31 plus L32 sigma 32 plus L33 sigma 33. So, you can go on writing the value for the stress component sigma 23 in the new system from the old system, knowing the directional cosines of the new set of axes. Now, we would like to consider another example to make you comfortable about the transformation. Let us consider example wherein we are interested in considering the stresses in 2 dimensions. Let us say that we have the stresses given in this system x, y, and we consider the new directions. Let us say the new directions are this is the direction, new direction, and let us say that this direction is 1 dash and this is the direction 2 dash. So, therefore, this direction 1 dash makes an angle theta with the x direction. So, therefore, we have the direction cosines Lij is given by direction cosine of this is nothing but cos theta sin theta and direction cosine of this direction 2 dash is sin theta cosine theta. So, herein it is 2 dimensional problem. So, therefore, I and j takes up value 1 to 2. Now, the transformation rule is going to be sigma m n l m I l n j sigma I j. Let us find out the component sigma 1 1. So, let us find out the component sigma 1 1. So, sigma 1 1 dash. So, we will indicate that sigma 1 1 dash. This is nothing but L L1 in L1 I L1 j into sigma I j. So, this is going to be given by L 1 1 L 1 j. I am sorry, this should be so we are taking the value of I to be 1. So, therefore, L 1 1 into L I j into sigma 1 j plus L 1 2 L 1 j into sigma 2 j. So, we can expand it further. So, this is equal to L 1 1 L 1 1 sigma 1 1 plus L 1 2 sigma 1 2 plus L 1 2 L 1 1 sigma 2 1 plus L 1 2 sigma 2 2. So, now we will try to substitute the value. So, we will get now, we will simply represent the stress sigma 1 dash as sigma 1 dash. This is going to be now, we have L 1 1 L 1 2 L 2 1 L 2 2. So, if we now substitute the values, then this is sigma 1 1 cosine square theta plus this is cos theta, this is sin theta. So, sigma 1 2 cos theta sin theta. Similarly, we will have this is sin theta, this is cos theta. So, therefore, it is sigma 2 1 cos theta sin theta, and this is nothing but sin square theta. So, therefore, sigma 2 2 sin square theta. So, this finally is nothing but sigma 1 1 cos square theta plus sigma 2 2 sin square theta plus, since sigma 1 2 is equal to sigma 2 1, we can write this thing as sigma 1 2 twice sin theta cos theta. This can be written finally that sigma 1 dash is nothing but, if we write this cos square theta equal to 1 plus cos theta by 2, cos 2 theta by 2 and sin square theta as 1 minus cos 2 theta by 2, then this will be given by sigma 1 1 sigma 2 2 by 2 plus sigma 1 1 minus sigma 2 2 by 2 cosine 2 theta plus sigma 1 2 sin 2 theta. So, we find that sigma 1 dash is given in this form, and if you want to write in the xy system, so if we represent 1 dash by x dash, 2 dash by y dash, and similarly 1 by x, 2 by y, then we can write the above expression in the form that sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cosine 2 theta plus tau xy sin 2 theta. So, this is the transformation that you have considered in relation to Mohr circle in 2 dimensions. Similarly, if we now consider the other stress component, so we would now like to consider the component of the stress which is going to be in the direction 2 dash. So, it will be, this is the plane we are considering, and so this is the direction which is outer normal. So, now we will get the component sigma 1 dash 2 dash. This is now going to be equal to, so it is again 1 I, n is 2 now 2 j. So, in fact, this dash has no meaning, we are just trying to consider the new direction 1 and 2. So, this is how we are going to get the link of the new system to the old system, and again we are going to have expansion of I first. So, it is L 1 1 L 2 j sigma 1 j plus L 1 2 L 2 j sigma 2 j. Now, we can write L 1 1 L 2 1 sigma 1 1 plus L 2 2 sigma 1 2 plus L 1 2 L 2 1 sigma 2 1 plus L 2 2 into sigma 2 2. So, all the 4 components of stresses are now involved, all sigma 1 1 1, sigma 1 2, sigma 2 1 and sigma 2 2. So, if we now try to collate them, noting the values of the direction cosines. So, if we look into the value of the direction cosines which were given earlier. So, we will have now this is cos theta, this is minus sin theta. So, therefore, it is going to be cos theta sin theta sigma 1 1 plus this is cos theta, this is cos theta. So, therefore, cos square theta sigma 1 2, and this is again L 1 2 is sin theta and this is minus sin theta. So, therefore, it is minus sin square theta sigma 2 1 plus here this is L 1 2 is minus sin theta and this is cos theta. So, therefore, this is sin theta and this is cos theta. So, therefore, it is cosine theta sin theta sigma 2 2. So, we can now write it sigma 1 dash 2 dash, which is nothing but the shear stress, and this is going to be minus sigma 1 1 minus sigma 2 2 by 2 sin 2 theta plus, since sigma 1 2 is equal to sigma 2 1. So, you can write this thing as sigma 1 2 cosine 2 theta. So, this is the expression for the stress, shear stress in the new coordinates, and if you want to write in terms of sigma x and sigma y, this is nothing but sigma x minus sigma y by 2 sin 2 theta plus tau x y cosine 2 theta. So, the new shear stress is given by this, and this is what again you have obtained in connection with the Mohr circle diagram in 2 dimensions. Just finally to look at the expression for the transformed x dash, and the shear stress is like this. And if you are interested in finding out the stress sigma 2 dash which is nothing but sigma y dash, we can make use of the fact that this is given by the stress invariant. We can make use of I1 minus sigma x, and this is nothing but sigma x plus sigma y, this is sigma x dash minus sigma x dash. The stress invariants are the same. So, therefore, we can make use of the fact that sigma x dash plus sigma y dash equal to I1, and that gives this. And finally, if you substitute the value of this sigma x dash, it will finally come out to be like this: sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cosine 2 theta minus tau x y sin 2 theta. So, therefore, that is the sigma y stress. So, finally, your new stresses are given sigma x dash like this and sigma y dash is given here and shear stress is given. Now, we would like to consider how to draw Mohr circle for stresses in 3 dimensions. You are familiar with the Mohr circle in 2 dimensions. So, we will now like to consider the construction of Mohr circle in 3 dimensions. We have the stresses at a point I j. Starting from these stresses, you must calculate the principal stresses sigma 1, sigma 2 and sigma 3. You can also calculate their directions. Now, we would like to consider an arbitrary plane with direction cosines L, M, N and the reference directions are sigma 1, sigma 2, sigma 3. So, on this plane we will have the normal stress given by L square sigma 1 plus M square sigma 2 plus N square sigma 3. We are also having the relation that L square plus M square plus N square equal to 1. So, if I substitute N square equal to 1 minus L square minus M square, that will give me sigma equal to L square sigma 1 minus sigma 3 plus M square sigma 2 minus sigma 3 plus sigma 3. So, let us consider this relation to be 1. Now, the tractions on the plane L M N is going to be given by L sigma 1, M sigma 2 and N sigma 3. So, if we now consider the total traction total traction S, which is going to be related to S1, S2, S3, the 3 tractions on the same plane, and the relationship is nothing but S square is equal to S1 square plus S2 square plus S3 square. Since S1 is L into sigma 1 and S2 is equal to m into sigma 2 and S3 is equal to n into sigma 3, we can write the relation S square is nothing but L square sigma 1 square plus m square sigma 2 square plus n square sigma 3 square. This type of relationship we have also derived earlier in connection with the determination of the maximum shear stress and also shear stress directions. Now, since the normal stress on the plane is equal to sigma, and if we try to consider the shear stress on the plane to be tau, then we can write S square is also related to sigma square plus tau square, and therefore we will have tau square is nothing but S square we will continue writing tau square plus sigma square is equal to L square sigma 1 square plus m square sigma 2 square plus n square sigma 3 square. Again, we will like to substitute the n square in terms of 1 minus L square minus m square. So, we will get tau square plus sigma square is equal to, we will have L1 square into sigma 1 square minus sigma 3 square plus m square sigma 2 square minus sigma 3 square plus sigma 3 square. So, this we can now rearrange. Tau square plus sigma square minus sigma 3 square is equal to, I am sorry, this is not L1, this is L only. So, this is L square sigma 1 square minus sigma 3 square plus m square into sigma 2 square minus sigma 3 square. So, this let us write this equation as equation number 2. I will show you that these relations 1 and 2 are the basis to draw the Mohr circle in 3 dimensions in my next presentation.